So, good afternoon, one and all, and welcome back to the class on tribology. So, it was a long gap in between due to holidays of Dasara and all. So, do you remember what we were dealing about in the last class? So, we had started basically hydrodynamic journal bearing, and the basic concepts were clear enough in last to last class. And later in the last class, we dealt about exactly what you mean by Petrov equation, how do we derive it, right, for coefficient of friction value. So we dealt about the Petrov equation. Before that, I showed you the concept of the viscosity gradient, how it will be across the top of the plate and the bottom of the plate. The top plate will be moving and the bottom plate will be fixed, right? So the relative velocity gradient will be varying. So when will be uniform and when it won't be uniform, we dealt with respect to the Newtonian fluids and non-Newtonian fluids, how the viscosity effect varies. So we dealt about the viscosity aspects as well. And then we went on for Petrov equation. So wherein we derived an equation for coefficient of friction associated in our journal bearings. And we made an assumption that the shaft will be concentric, even though sometimes the shaft might not be concentric, but the assumption was taken care enough. So based on that, we derived an Petrov equation to know the coefficient of friction value for the journal bearing. And also we related to the Samford number. What is it basically, right? So I think until here we had done. And also we discussed about the stable lubrication. What happens if in case the variation is with respect to thick film of lubrication and thin film of it. And the terminology of this journal bearing was done in the very beginning class, right? And I had given you a brief output related to the hydrodynamic theory concept, what you are supposed to understand before deriving the Reynolds equation for two-dimensional flow. And we had discussed what are the assumptions one has to follow for deriving the Reynolds equation. So it was like totally a mapping of the experimental data with a mathematical approach. So experimental data on hydrodynamic theory was developed by Mr. Tower, and Mr. Reynolds developed a mathematical model to compare the experimental data of hydrodynamic theory. And hence the mathematical model equation what he derived is termed to be as Reynolds equation. So he made some set of assumptions what we had discussed in the last class. So if I want to just brush out before starting with the Reynolds equation. So here the assumptions were as follows. It is assumed that the film thickness is very small in comparison to the radius of the bearing. So obviously the film thickness will not be very too high in comparison to the radius of the bearing. So that is what been assumed here. And hence, due to this very small value of thickness, it is therefore the curvature which is across the radius of the bearing and the film could be neglected. So this was the first assumption what was being followed by Mr. Reynolds. And second thing which was told that the lubricant what he used is of basically a Newtonian fluid, wherein if it is a Newtonian fluid, the viscosity will remain constant irrespective of what pressure it's been applied on it across the contact area. Apart from that, they assume that it is an incompressible type of lubricant and its viscosity remains constant. And one more assumption what they followed is the forces which come across due to the inertia of the lubricant will be neglected. It can be a minimum value. So it is not being considered and it is considered to be as a neglected aspect. So any forces which is coming across due to inertia across the lubricant film will be neglected. And one more thing, the pressure associated with the lubricant film is assumed to be constant in both the direction, in axial as well as the vertical direction. So this was the next assumption being made by Mr. Reynolds. And further, it was assumed that the bearing which has been used can have an infinite length across the axial direction. And here no side leakages. Leakages can come across in between while the bearings are revolving, but still the leakages related to the lubricant is assumed to be neglected. So no side leakages. And hence it is an uniaxial direction what we are following. I told you in the very beginning, if we assume like bidirectional, then it will be very complicated to derive either it is an Petrov equation or hydrodynamic. And hence here always the side leakage is assumed to be neglected so that it will be an unidirectional one across the axial direction, and the length of the bearing could be an infinite one. So this was the assumption made. And lastly, the velocity of any particle in the lubricant. In the lubricant, you might be having the particles which might be the asperites which come from harder material to the softer material, or it could be any material particles which come in between as an additive or as an any active material, or to keep the lubricant as per the desired property. So any other contamination. So whatever might be the particle which is embedded in the lubricant, the velocity of it mainly depends upon the x and y coordinates only. So these were the set of assumptions made by Reynolds in order to derive the Reynolds equation to map with that of the experimental data which was conducted by Mr. Tower. It's not like he invented some new thing. No, experimental approach was there already. So he just wanted to validate the experimental approach on hydrodynamic theory, and hence he derived a mathematical model. For that, the equation what he concluded was given as a Reynolds equation. So this is about the concept of hydrodynamic theory. And before going into, you just want to see how the like pressure distribution. Suppose if you have the inlet here through which the lubricant oil will be spilled out. So this will be our journal or the shaft, and wherein you will be having the bearing casing here. In between, you will be having the clearance in which the oil will be spilled out. So you will be having the thickness of a lubricant film over here. Okay, so this is the direction in which the journal will be rotating. And this is the level of the lubricant in between the journal and the bearing surface, the clearance value in which you have the level of lubricant filled in between these two. So this is the diagram what you have to understand, in which direction the journal is bearing and the level of lubricant, right? So this is just an cross-sectional part of our journal bearing. So with respect to that, the pressure distribution curves you should just understand. So here you can just see the length of the shaft here is the bearing can be considered to be as 6 inch, and wherein the diameter of the journal is considered to be as 4 inch, and the journal is rotating in this direction. So this is the clearance in between the bearing surface and the journal. So at the tip, the pressure point will be 0, and at the upper line, it will be the maximum. But it will be an uniformly distributed pressure across the surface in between the bearing as well as the journal. Okay, so this is how the pressure distribution has to be distributed uniformly. So, and you should be knowing where the value of P is 0 and where the value of P is maximum. Okay, so this is just to show you and make you understand about the pressure distribution curve, right, for your better understanding. And you know what you mean by a Reynolds equation? Basically, it is termed by the person Mr. Reynolds, and this basically gives you a partial differential equation. So this equation will describe how the flow of the lubricant film it is, and it is mainly assumed that the lubricant film what we use will be very thin. So we specify here that this equation will describe the flow of the thin lubricant film between the two surfaces. So one is our journal and other one is the bearing surface. So in between these two surfaces, how the flow of the lubricant will be. So that will be analyzed and described by the Reynolds equation. So it is obtained by partial differentiation, and hence it is called to be as a partial differential equation. Okay, so after deriving this mathematical model, he found out basically that hydrodynamic pressure, okay, so which is peaked at a particular value, will be always behind the center of the contact, and that of efficiency of the lubricant depends on viscosity, speed, and bearing dimension. Just don't crack head more on it. So what you have to understand that the hydrodynamic pressure will be very sharp, okay, and it has the highest peak value. It will be just behind the center of contact. So this hydrodynamic pressure we have studied already in the previous classes. So where I've told that whenever you have two rolling components, your sliding components, mechanical components which are either sliding or contact, the pressure will be highest at the backside of the contact area of contact. The same thing is applicable to the journal bearing here also. So hydrodynamic pressure will be maximum at the backside of the center of contact between the bearing as well as the journal. Okay, so this is a main thing what you have to keep in mind while deriving the equation. And it is also been told the efficiency of the lubricant what you are using mainly depends upon what is the grade of viscosity of that particular lubricant. Okay, so what is the speed with which the fluid is in moving, and about the bearing dimensions also, because you'll be having a journal, and also it depends upon what is the dimension of the bearing. Is it too big, yeah, too small, yeah, medium structure, what is the film thickness you'll be using, and mainly we have assumed that you should be having a very thin lubricant film. So all the things, these parameters will mainly affect how well the lubricant can provide a smooth flow with reduced amount of wear and friction. That shows how efficient the lubricant is. And this efficiency mainly depends on viscosity, speed, and bearing dimension. So these are the things you have to keep in mind. Okay, so these are just the prerequisite data what you have to understand. So before this there were, yeah, one more diagram here I just filled out. Yeah, so this you have to understand. So you know that in Reynolds equation derivation, we assume that the lubricant should be very thin film, and it is also assumed that since the like hydrodynamic fluid film is of negligible thickness, so even the radius curvature part could be neglected. So we are assuming that thin film lubricant, along with that the bearing radius curvature will be neglected. In that case, it will be replaced by the curved bearing. Means, sorry, the curved bearing will be replaced with the flat bearing. So you could have the bearing of a curved one or a flat bearing. Since it is a very thin film, and that film will be so thin that it will not like affect more in between the curvature of the surface of the journal and the bearing, and as a result the curved bearing here will be replaced by a flat bearing. So here you can see a very small partial bush which has been supporting for the flat bearing surface, and here you will be having the rotating journal. So this end will be fixed and this will be movable part. So this is the section of the journal. A small cross-sectional element of the journal is being taken here. All right. So this is our journal, and this is our bearing surface, and in between we have an lubricant film over here. So a small cross-sectional area of the lubricant has been taken here. So this shows the direction with which the lubricant has been flowing. Okay. So here also you can see the velocity with which it is moving. So we studied about the velocity distribution and all in the very long back, right? So if you go back to this equation, you'll just remember where it is. No, after this only it was. Yeah. Okay, I think it was in previous some other. Okay, fine. So we'll discuss with this only. I think there was one slide what I have missed here somewhere. Fine. So what we basically do here is we have just taken a small lubricant film cross-sectional area, and it shows the direction in which the lubricant has been flowing, right? So this is the maximum height. So H is the thickness of the film of the lubricant, right? So again, it depends with what speed it moves in. It again depends upon the speed with which the journal is been rotating, right? So here, with respect to the direction of the flow, the amount of pressure with which it is moving you have to consider. So here we use the coordinate system, so be careful. So this will be the x coordinate, and this will be the z coordinate, and this will be the y coordinate. So the direction of the flow here is being with respect to the coordinate system, which is being shown over here. So when the flow is in this way, the pressure also will be in the same direction, right? So with what pressure it is moving, so that will be given with respect to P into dy into dz here. Because it is moving along the x direction, you will be taking the parameters associated with y and z. So this is the direction what you have to show. And similarly here, when you are having a flow of lubricant in this direction, you'll be getting some opposite like the force which is coming in the backward direction. So while showing that, it will be in an opposite direction where you will show the pressure P plus the variation in the pressure with respect to the x coordinate system into dx, and the whole thing will be multiplied by dy into dz. So this is for opposite direction. And here the shear stress comes into picture. Why? Because the plate is moving here, and here the plate is held stationary. You have a supporting bush. The plate, in the sense, you have a journal here which has been rotating. Since the journal is rotating, the fluid which will be moving will move along the direction in which the journal has been rotating. And due to this, a shear stress will be generated across the surface where the journal is rotating. And hence you have to add on here the shear stress value, how the shear stress is varying with respect to your y-axis. And again you have to write down dx into dz. So this also will be in the direction in which the flow of lubricant is. So this is what you have to understand. And again the shear stress here across the stationary surface. So related to the partial bushing surface, there will be a very mild shear stress. I told you that the velocity gradient, if it is a Newtonian fluid, right, and the flow is uniform, then what we say, it will be moving with an uniform velocity gradient. Suppose if you have one plate fixed and one plate moving, so then there will be change in the amount of the velocity gradient it is moving. So that depends upon what is the height from which your element is, basically from the stationary surface to the value where you have to measure the shear stress. So based on that distance, you will calculate the shear stress you are getting. But the maximum shear stress will be across the surface where the journal is being rotating. So this you will write down. But here, due to stationary surface, you will be having an shear stress in the opposite direction, because if you want to get shear, it has to slide against opposite direction, right? So then you will write tau into dx into dz. So and you will show the direction in opposite. So this is the concept of the flow of the fluid with respect to the pressure, and the shear stress will come into picture because the journal is rotating. So you have to figure out what are the values of the pressure you get with respect to the coordinate system, and what are the shear stress values you have to write down with respect to the journal which is rotating in the given clockwise direction. Okay, so like you have to just figure out the sketch first, show the flow of direction for the velocity gradient with respect to the rotating journal, and then you have to come back for summation of all the forces along the x direction. Okay, so summation of all the forces along the x direction. So what all forces you have, so you have to see. So the first one is related to P into dy dz, dou I, yeah, dou z. So you will write the first term P into dy into dz. Next, you have like 3 to 4 more forces what you have to take. But this here, it is coming in opposite direction. So this will be minus of P plus dP by dx into dx multiplied into dy into dz. So you will write down the value over here. Since it is coming in opposite direction, you'll put the sign as minus. After that, now you have to give the values of the shear stress force which is coming. So this is coming in positive direction. So you'll write plus tau, open the bracket, write tau plus dou tau by dou y into dy, close the bracket, again write dx into dz. Okay, so that will be the positive direction what you have to write on. So you will write this value, right? And yes, there are two parameters. They have taken the common. Just a second. Yeah, this is written here. After that, you have one more torque which is coming in the opposite direction. So this we have written, which is a positive term, and then you have to write this as negative. So minus 2 dx dz. That will be equal to 0. So you will add on all the forces which is coming into picture in x direction. So you will be having two forces due to pressure and two forces due to the shear stress. So in that, so this will be positive. The pressure force in this direction will be positive, and the shear stress and this, which is associated here, will be positive, and these two will be the negative forces which is coming along the x direction, and hence you will equate that all equal to 0. So then you will simplify the equation. So when you simplify the equation, you will see that it is given like the pressure variation with respect to x will be equal to the variation in the shear stress with respect to the y direction. So you will, after simplification, you will end up with the equation dp by dx is equal to dou tau by dou y. So this is the equation what you come that shows that the amount of pressure which is exerted by the lubricant in the direction of x will be equal to the shear stress which is developed in the y direction. So when you have a shear stress along the y direction, obviously that amount will be equal to the amount of pressure which is induced in x direction. So that pressure induced in x direction will be proportional to the value of strain. So if you plot and graph of stress versus strain, so stress will be taken along the y direction and the strain will be taken along the x direction. So that is nothing but here the dp by dx. And apart from that, we have derived this equation already. The shear stress is equal to mu into dou u by dou y. So we derived this with respect to our viscosity equation also. So wherein the shear stress will be directly proportional to the velocity gradient with which the lubricant is moving. So if you want to remove the proportionality symbol, you have to use a constant, which is the viscosity value. So the shear stress mainly depends upon what is the grade of the viscosity of the lubricant you are using and with what velocity gradient it has been moving, right? So this is the equation what we have derived already in the previous classes. So now using this equation, what we do is you will substitute the value of tau here. So you have dp by dx is equal to dou tau by dou y. So go back to this equation. In place of tau, you can write mu into dou u by dou y. So how the equation changes then? The equation for the change in pressure with respect to x direction now will be changed into mu times dou square u by dou y square. Why? Because you had dou tau by dou y, and tau is nothing but mu into dou u by dou y, right? So you will write here mu into dou u by dou y, but you had dou u by dou y here already in the shear stress equation, and hence it becomes dou square u by dou y square, and the same viscosity value here you will retain. So now we have changed the equation to the shear stress equation, okay, and hence dp by dx will be equal to mu into dou square u by dou y square. So this is what the equation will look into. So after that, if you just what we say. So now you have dp by dx is equal to mu into dou square u by dou y. So now if you start integrating it, so if you integrate this equation, so then you will get dou u by dou y is equal to 1 by mu into dp by dx. In terms of y we are integrating, so you will get one constant value which is c1. So this is now being integrated. So once you get this equation, so what you can do is you can find out the value of u. So to find out the value of u, you have to again integrate. So when you integrate it, so you will again integrate this entire equation. So it will be dp by dx when you when you integrate y, so it will be y square by 2. So this 2 will come here. So you had a constant here again. So it is c1 into y plus you will get one more integral constant. So this is how the equation now reduces to find out an equation for velocity distribution. So how the velocity is being distributed in the given journal bearing when the lubricant film has been moving. So this will be given by this equation. So once you are thorough with the diagram and sketch, you can just add on all the forces along the x direction and then simplify it, and then use the shear stress equation what we have derived before using the viscosity concept. So then you substitute the value of tau back to the equation here, then dp by dx will get changed, and then start integrating twice, and then you will get the value of u, which is the velocity distribution value. Okay, so this will be the equation for velocity distribution. So once this is done, now you have to put some assumptions. So what are the assumptions you put is so this is the equation, right, previously. So now you have to know the values of constant C1 and C2. So now what you will do, we will put initially y is equal to 0. If y is equal to 0, then u also will be equal to 0. So this is the first condition, and then you will find out the value of C1. So if you go back to the equation and put y is equal to 0, right? So you can get the equation reduced, and you can get the value of C1 is equal to this much. So at that case, your C2 don't have any values related to y and u, and hence obviously this will be equal to 0. So after you know the equation for C1, you can come back to this equation here and replace the value of C1 by u by h minus h by 2 mu into dp by dx. So you will substitute the value of constant in the equation. So when you substitute, then the velocity distribution equation gets changed again. Okay, so after substitution, you can remove the common factor because you have dp by dx here also, and initially here also you had dp by dx. So you can take the common factor outside, and you had 1 upon 2 mu in C1 value, and also you had 1 upon 2 mu in the first term. So you can take 1 upon 2 mu as a common factor. dp by dx is also the common factor. So the remaining part here is y square. So you will write it as y square here. And when you have taken 1 by 2 mu into dp by dx outside, right? So you can retain the value which is remaining here as h into y, and plus you will be having u h by y here. This is a separate part, so you will take it as u by h into y. So now this is how the equation gets changed, because you cannot retain the equation with respect to the constants. You should find the value for the constants. So usually after getting the equation, we will derive the values for the constant, and we'll substitute those constant values, and we will simplify the equation again to get the required velocity distribution equation. So this is how you have to get the velocity distribution equation. So once velocity distribution equation is done, we can go for Reynolds equation, right? So before going that, you should just understand the values here, how the velocity distribution, this one thing has to be understood. So here you will be having the rotating journal. right? So this will be the speed with which it has been revolving. And you have a stationary bush. The plate, what we are telling stationary plate, it has been nothing but the stationary bush. And this is the rotating plate, which is nothing but our rotating journal, right? And this is the direction with which the lubricant is moving, and this is the height of the, mean to say, the thickness of the lubricant film. So if you have thickness of the lubricant film, then at this surface it will be moving with an uniform velocity gradient of u, because it is nearer to the moving plate. Suppose if you want to find out the velocity gradient across a particular point here, then you can say that it will be moving with some velocity gradient, and that will vary with respect to the distance which is away from the fixed plate, right? So it will be dou u by dou y, small dou u by dou y. This will be the velocity gradient with which the fluid will be moving at this particular point. But here it will be moving at an higher velocity gradient, and since it is very nearer to the rotating part, it is the capital U what we refer. But as the different layers of the fluid will come down nearer to the fixed plate, it will be moving with some velocity gradient which will be lesser than that of the velocity with which it has been moving across the contacting surface of the moving plate. So that you have to understand. So with respect to that, the thick line here will show that the dP by dx, the pressure dP upon dx will be usually greater than 0. And this dotted line will show you that the variation of pressure with respect to x will be equal to 0 in this case. And in this case, dP by dx. Okay, so it depends upon how the velocity distribution is coming into picture. So it could be like the distribution could be in the parabolic, yeah, it could be in a linear way. Okay, so depending upon how the velocity has been distributed, it could be greater than 0, it could be equal to 0, and it could be lesser than 0. And all the three nature of the velocity distribution is shown here. So in this trend, the pressure distribution will be lesser than 0, it will be a negative value. And here it will be exactly the variation, the pressure distribution here exactly will be 0 with respect to our x coordinate, and again with respect to our dx, the value of the pressure will be greater than 0. Okay, so these are the velocity distribution curve, what you have to understand before going. So when you have pressure is maximum, so you can tell that when dP by dx is equal to 0, when the velocity gradient is equal to capital U upon h, the pressure will be maximum, because it is taking the entire thickness of the film here. It is not some particular height. If you take some particular height, then that is this small y. So here by taking the total velocity gradient which is moving across a rotating journal, so it is u upon h into y. So in this condition, the pressure will be equal to maximum. So this is what you have to understand about the distribution of the pressure with respect to velocity distribution as well. So once this is done, so now we can go for Reynolds equation. So now you know about the velocity with which it has been moving. So now you will write like Q is equal to integral of O to H into U times dy. So O is nothing but H will show you the thickness of the film, and U will be the velocity with which the film is moving, and that will be differentiated with respect to Y. So when you integrate this with respect to the limits 0 to h, then you will derive with this equation. So later you will equate this equation to 0. So when you equate this to 0, the equation what you have should be here equal to 0. So how does this change here? So dq by dx is equal to 0. So now we have to differentiate q with respect to x again. So then you will get u by 2 into dh upon dx, because you are differentiating q with respect to x. So u by 2 is constant. You will write dh by dx. And again minus, then again this has to be differentiated with respect to d by dx. So what you will do this, the whole thing will be differentiated. H cube by 12 mu into dp by dx has to be differentiated. So when you differentiate this term, so this will be equal to the value of 6u into dh by dx. So sorry, so this has to be simplified here, d by dx of h cube by 12 mu into dp by dx. So later this value will be reduced into h cube by mu into dp by dx. So this h cube by mu into dp by dx, when you differentiate, you will get 6u into dh by dx. So after that, so this is termed to be as an Reynolds equation, what you get for one dimensional flow. So dou by dou x of h cube by mu into dp by dx will be equal to 6u into dh by dx. So this you will get after simplification. So here the simplification process is not done. So after this equation, you will simplify here. After simplification, this will be the last term what you get, and this will be the basic classical Reynolds equation for one dimensional flow. Actually derivation complete is a very bigger way which has to be described, but when it comes to derive a Reynolds equation for two dimensional, you should speak what is Reynolds equation, and then you should explain the velocity distribution which occurs in journal bearing, and then you should show the classical Reynolds equation, how it comes forward. And this is only for one dimensional flow. So if you consider the leakages, then it will be for two dimensional. So with side leakages, the equation will get changed here. Why? Because you will be taking with respect to x and with respect to z also. Okay, so you will be having the same thing here, dou by dou x, h cube by mu into dou p by dou x, plus you will be having the extra component here for the leakage, which will be dou by dou z into h cube by mu into dou p by dou z. So this will be equal to 6u into dou h by dou x. So this will be the complete classical Reynolds equation for two dimensional. If the leakages are assumed to be neglected, then this will be the reduced form of Reynolds equation. So along with that, one important approximation solution what you have to understand is by Sommerfeld. So we have derived an Sommerfeld number by with respect to the Petrov equation before also, right? Sommerfeld number we derive with respect to the coefficient of friction for Petrov equation, which is r by c whole square mu n upon p, which is the Sommerfeld number. Okay, so similarly here you have to get it for Reynolds equation also, and by approximation method, the Sommerfeld equation for Reynolds will be r by c into f, that will be equal to phi into r by c whole square mu n upon p. So this we have got this number already in Petrov equation. So same thing has been equated here. So before ending, you should tell that this term is the Sommerfeld number, and this phi will be nothing but the functional relationship which comes with respect to the Reynolds number. Okay, so this is how the Reynolds equation has to be related with that of Sommerfeld number. So where phi will play an important role to get the required functional relationship. So this is about the Reynolds equation. If they ask you to derive for two dimensional, you can end up in one dimensional, and you can show that if the leakages are included, so this will be the equation for two dimensional one. And later related to this, by approximation method, the Sommerfeld equation will be this one. In this, the Sommerfeld number is the component r by c whole square into mu n upon p, which we had concluded already in the previous slides related to the Petrov equation. Okay, the same number is being taken over there. It is now a new quantity what we have added. The same thing which was there is being considered. So this is about Reynolds equation. what you have to understand. And later, yeah, I have 10 more minutes. So design considerations you have to follow. So now you know like what you mean by Petrov equation, the viscosity part, the velocity distribution, how the pressure is distributed uniformly, and how to derive an Reynolds equation, right? Apart from that, we dealt about the terminologies with respect to the nomenclature of a journal bearing, and also the classifications, applications of it, everything. So now it's the time for considering the design considerations, what you have to follow to design a journal bearing. So for that, these are some design considerations what one has to follow. So here you have to see that the variables, either it should be given or under the control of the designer. So if you want to design, it has to be controlled by the designer, or the data related to this has to be given already. So one thing is the viscosity. You should be knowing what is the viscosity of the given lubricant. Okay, and what is the load per unit of projected bearing area. So you will be having a bearing area on which the amount of load is subjected. So what is the effect of the load per unit area or cross-sectional area of the bearing? So that will be nothing but P, which will be providing us the pressure distribution. So we studied the pressure distribution. So it will be uniformly distributed. So you will take a cross-sectional area of the bearing, and if you subject some amount of load to it, so how the pressure is distributed across the bearing area. So that you have to understand, and the value of P has to be given, or it has to be under the control of the designer. So based on the model you have to manufacture, you can fine tune with the pressure values, and these pressure values mainly depend upon the load, right, which has to be subjected. And also journal bearing as high load bearing capacity, right? So basically, depending upon the amount of load you are applying, the pressure gets varied. So based on the application, you have to see that which is the minimum, yeah, maximum load you can give for the bearing, so that there will be no large amount of wear or friction associated with, because we use an lubricant of very thin film. And even the assumption is the same thing while deriving the Reynolds equation. So you should be careful about the load which will be subjected. Apart from that, what is the speed with which the bearing will be, the journal will be rotating, right? So that also one has to be clear enough, and the data has to be given. Apart from that, the bearing dimensions has to be known. The length of the bearing, the angle beta, and the clearance value, and the radius of the shaft, right? So this all thing has to be known. So these are the variables which has to be directly given, or which is under the control of the designer. Apart from that, there will be some variables which are dependent, that cannot be given directly. So based on the given data, you should be able to find out the dependent variables. That also shows the performance factor of that particular bearing. So based on the given data, we will be determining these values. So what are this? The mainly first one what we determine is the coefficient of friction. What is the temperature rise which is coming in when you are making the bearing to work, right? So like, and thirdly, what is the volume flow rate of the oil, which is given by the letter Q. So you will be determining the volume flow rate of the oil. So this is again, we get from the Reynolds equation directly, and also the minimum film thickness. So in nomenclature, we had studied what do you mean by H naught, what is R, C, beta, and L. So these are all related to the nomenclature of the journal bearings. So all these data has to be given to determine the performance factors. So the performance factors here are nothing but the coefficient of friction, the temperature rise, the volume flow rate of oil, and the minimum film thickness, which is H naught. So these are the design considerations one has to keep in mind before designing it. So there are some rules and norms what we have to follow for design as a thumb rule. So that I will do it in the next class. So before that, you should be knowing some other concepts. the terminologies basically. Okay, so when it comes to the angular speed of an journal bearing, so how do you determine the angular speed, which is n? Because we are telling that here the n should be given, right, or it should be under the control of the designer. So if the designer want to control the speed n, so what you will do basically, so it depends upon the hydrodynamic film bearing performance exactly. So if you want to know the angular speed n, so that will be obtained by this equation. So this will be equal to n suffix j plus n suffix b minus 2 into n suffix f. So what does these values are? So n suffix j will give you the journal angular speed. Okay, so what is the angular speed with which the journal is being revolving? Okay, so this is given by n suffix j. J itself will show the angular speed of which is of journal. Similarly, if it is n suffix b, it is the angular speed of the bearing. So this will be the value for n suffix b. And finally, n suffix f means you'll be applying some load right across the contact area, so where the pressure will be distributed. So you should know the speed with which the angular speed with respect to the load. So this will be nothing but the load vector related to the angular speed with what it will be revolving. So this is given by n suffix m. So if you substitute all these values, that will provide you the angular speed. So with respect to the diagram, you should be able to understand. So here you can see the lubricant film, right? So it is the direction in which the n suffix j means it is a direction in which the journal is revolving. So this is the amount of load which has been subjected, right? So here, if the journal has been revolving, so it shows that it is just showing the angular speed of the journal and not the angular speed of the bearing and not the angular speed of the force or the load vector, right? So in this condition, NB will be equal to 0 and NF will be equal to 0. So in that case, if you substitute this equation back, then we will get that the angular speed will be directly equal to the angular speed of the journal. So this will be satisfied only if the angular speed of the bearing and the angular speed of the load vector is 0. At that case, the net angular speed will be equal to the angular speed of the journal. So this is what you have to understand. So by looking into the diagram, you should be able to understand. If they show you a direction here as some angular speed with which the bearing is rotating, then you will be having the value for bearing. Okay, so here you don't have, if you in this sketch, you can see that you have the speed, angular speed with which the journal is rotating. You don't have the angular speed with which the journal is rotating, but you have the angular speed with which the load vector is revolving. So the load vector will revolve due to the subjection of the load, right? So here the value of NF will be known. And again, the angular speed of the bearing is unknown. So you'll substitute back in the equation. So you'll write the angular speed of the journal as NJ. You will write the angular speed of the load vector as NF. It is into 2, but you don't know the value of angular speed of the bearing. So this value will be 0. So finally, angular speed N will be equal to Nj minus 2 times of Nf. Okay, so this is the value what we get when you have the known values for the journal as well as the load vector with respect to the angular speed. Again, every time you can see the values, and here it is given. Here you can see that the angular velocity of the journal is given, and again the angular velocity of the load vector is given, and the angular velocity of the load vector is equal to half the times of the angular velocity of the journal bearing. So NF will be equal to here Nj by 2. So the load vector angular speed is now represented in terms of journal bearing angular speed. So here it is given that NF will be equal to 1 by 2 into Nj. So in place of NF, we can write N suffix J by 2. So now you know the angular speed of the bearing, sorry, you know the angular speed of the journal and you know the angular speed of the load vector. So you'll substitute back in the equation. So Nj, you will write it as it is, Nb is equal to 0, and here in place of Nf, you have to write Nj by 2. So 2 into Nj by 2, 2 gets cancelled. So the equation reduces to the total angular speed N will be equal to Nj minus of Nj minus of Nj. So both gets cancelled and it becomes 0. Okay, so whenever the value is given half the speed with which the journal is revolving, obviously the net angular speed will be equal to 0. So this is what you have to understand. And in the last diagram, you can see that they have given you the angular velocity for the journal as well as the angular velocity for the bearing, but not the value for the load vector, and hence nf will be equal to 0, and then you will write nj plus nb, and here the condition is nb is equal to nj. So in place of nb you will write nj and you will be having one more nj. So nj plus nj, then the angular speed will be the twice the angular speed of the journal, because the speed with which the journal bearing is rotating is assumed to be the same as the speed with which the bearing is rotating, and hence nb will be equal to nj. So when you substitute that in the equation, so n will be equal to twice the speed of journal bearing, so n will be equal to twice n suffix j. So by looking the diagram you should be able to see what is the angular speed and how to calculate it, whether all the three parameters are given. Yeah, only the speed of journal is given. Yeah, only the speed of bearing is given. Yeah, the speed of load vector with the bearing. Yeah, the speed of load vector with the journal is given. So based on that you will calculate the values. So I'll just end up here. So next you should know the Trumpel's design criteria. So after knowing the design criteria we can proceed further. So now if you have any doubts you're free to ask me, and in the same time kindly do write your name and USN in the chat room. If anyone have not written until now, kindly do add it on. Is it clear? Any doubts until now? Any doubts? Kindly reply. Any doubts? Is it clear? Are you people there? You're sleeping. Hello. How will I? Yeah, how will I come to know? Are you people there or not? You should ask something. Right? Yeah. So Akhil KV, okay. Anil Kumar.
Present, ma'am.
Ankesh Aman.
Yes, ma'am.
Gautam Krishna. Gautam Krishna. Absent. Balaji VR.
Yes, ma'am. Ma'am, Gautam.
Where were you?
Ma'am, I was switching on the mic, ma'am.
Okay. Balaji VR. Balaji VR is not there. Beldar Mohammed.
Present, ma'am.
Chaitanya.
Present, ma'am.
Chetan Kumar.
Present, ma'am.
Dheeraj.
Present, ma'am.
Ishant. Okay. Harshit S. Harshit. Harshit is not there. Himanka. Okay. Kanishka.
Yes, ma'am.
Nagamurli Krishna. Okay. Kunal Raj. Kunal. I think it's not there. Dhanush. Mohammad Ayan. Mohammad Ayan, you're there? No. Mohammad Junaid.
Present, ma'am.
Okay. Shri Prasad. Shri Prasad. Shri Prasad is there? No. Niharika. Niharika. Absent. Nihar Venkat Sai. Okay. Nikhil. Yeah. Nikhil R.
Yes, ma'am.
Neerav.
Yes, ma'am.
Prajwal.
Present, ma'am.
Rishabh Pandey. Okay. Rohan. Rohan is not there.
Ma'am, which Rohan? 59 or?
17ME042. Rohan Kaglakar.
No.
Okay. Roshan Yadav.
Yes, ma'am.
Suman Sagar. Suman Sagar. Absent. Sagar Dutt Mathur. Sagar Dutt Mathur. Sagar GB. Sagar. Okay. Sanjay Raghav.
Present, ma'am.
Shobit. Shobit is not there. He is not regular to the class. Inform him to call me up. Siddharth B.
Present, ma'am.
Siddharth Sridhar.
Yes, ma'am.
Subramanya.
Present, ma'am.
Tirumani Sethi Rohan.
Yes, ma'am.
Ulas.
Present, ma'am.
Vidyan. Vidyan. Absent. Varun.
Yes, ma'am.
Varun, you call me back after the class. Pavan.
Present, ma'am.
Danush.
I'm present, ma'am.
Dhyanesh. Okay. Gunasagar. Gunasagar. Meghanatha.
Present, ma'am.
Rasik Baran. Rasik Baran. Absent. Shiva Krishna. Shiv Krishna. Okay. Shreyas. Shreyas L. Absent. Srinivasulu.
Yes, ma'am.
Yogananda. Yogananda, you're there? Kiran R. Kiran. Ranveer Singh Chauhan. I don't know what's the problem with him. He does attend the test, that's all. Gautam Sai. Gautam Sai. Abdul Khalik Pasha.
Present, ma'am. Yes, ma'am.
Yeah. Shiv Pavan.
Present, ma'am.
Alok M.
Yes, ma'am.
Yeah. Thank you then. Take care. Have a nice day.
Ma'am, Gunasakar, ma'am.
I didn't call your name.
No, ma'am. I was there, ma'am. Suddenly I got disconnected and I rejoined, ma'am.
Gunasagar, what's your USN number?
Give me 402.
402.
Yes, ma'am.
18ME 402.
Yes, ma'am.
Yeah. I have marked your attendance.
Okay, thank you, ma'am.
Anyone else I have skipped out? Okay, I hope all have written your name and USN in the chat room. If still you haven't written, kindly do add it on. Take care and be safe. So let us meet in tomorrow's class then again.
Thank you, ma'am.
Yeah, thank you. Bye-bye.